welcome in. All right, so grade 11, this is a test on dynamics, which is really just forces. So it's kind of the first part of dynamics. And so here are 7 questions I'm going to go through, and I think this test is definitely one worth taking a shot at. So I'm going to put a link in the show notes, okay, so in the description, so that you can download the PDF of this test. You can try it, come back, and then take a look at the solutions. All right, so let's take a look. So one thing that I'll try to do, I may or may not be consistent, okay, on the test, but okay, we'll try to round our final answers to the same number of significant figures as the measurement with the lowest number of significant figures. I'll put up a link up above there for significant figures, just a reminder for you. And I'll try not to round in intermediate steps, right? So, or at least I'll keep quite a few decimal places if necessary. All right, so here's question number 1. So draw a free body diagram, okay, so for each of the 2 cases here. So the first case is a cyclist who fell off his bicycle and is skidding on the ground. Okay, so this is basically all about friction, right? We're going to be neglecting air resistance. So in order to draw this free body diagram, okay, so it's not going to be super difficult. Now, how you draw the free body diagrams is ultimately up to you. If you draw squares, rectangles, okay, or even circles. I'll draw a rectangle in this case. And the free body diagram, okay, so how it will look like, maybe I'll give this a little bit of space here. So you typically will try to draw, I mean, you definitely should start if you are, ever, unsure on where to start. Always remember that there's a force of gravity, which is basically the weight of whatever object you're dealing with. In this case, it's the cyclist. That force of gravity, okay, also is going to have a normal force, okay, on if the actual object is touching a surface, so whatever surface it is on, well here if it's the ground that it's skidding on, so there will be that force of normal. Then, okay, so what you have is you're going to have to put all your horizontal forces. Now the only horizontal force that we have here, because you have a cyclist skidding and we're neglecting air resistance, although even if we had air resistance, both of them are going to be against motion. So you have to pick, here it doesn't say, which way this particular cyclist is moving. So I'm going to, okay, just put this, okay, and this is the motion direction. So I'll assume that it's to the right. But it doesn't matter which way you assume, your teachers should know with respect to this motion, okay, how you're going to designate your friction. So your friction is always opposing the motion in this case. Okay, so here it is, and this is going to be the force of friction. Now, we don't know any of the values for here, so it's just a free body diagram, and that's the best that we can possibly do. There is no other force that we have present. So basically, yes, the motion is to the right in this case, and the cycle is skidding until eventually they're going to stop because the friction from the ground is going to, cause enough friction that eventually you're going to decelerate to a stop. So that's number 1, or at least part A. Let's take a look at part B. Maybe I'll switch colors here. A box is sliding down a ramp. Okay, consider all possible forces. Okay, so if we're going to have a box, I'm going to steal this one actually. So let's duplicate it. So here's our box skidding down. It's going to be at some angle. Now we don't know what this angle actually is. Okay, so, this is going to be on a surface. It's going to, okay, so here's my ramp. This would have been at some particular angle. So typically that will be given. In this case, they're only asking for a free body diagram. So I guess we don't really need that angle per se. So now, what are going to be all of the different forces that are present? So again, you will start with the force of gravity. So if you knew what the actual box, what that particular box weight was, or maybe mass, then you can find out what that force of gravity is. Here's the only tricky part, and sometimes students kind of miss this. I certainly did when I was just beginning physics. The force of normal is always actually perpendicular to the surface that an object is on. So the force of normal is really the kind of the reaction force that you have Okay, so that whatever object you're carrying is not going to fall through the ground. So, going back to that first original question, if this was, if this cyclist was skidding on the ground here, so I'm going to bring this back right there, that's why the force of normal was upwards, because it was going to be perpendicular to the actual surface that it's touching. So here, if you have this, perpendicular will mean that it's not going to be up, but it's going to be kind of at an angle, okay, like so, but it is perpendicular. And what I mean perpendicular, it's perpendicular to this particular surface. So that's going to be your force of normal. And, let me just switch this out of here. Oops. I'm going to shift this out so it doesn't block us. So this is going to be your force of normal. And again, it's perpendicular right there. So you can do that, or, you can put it right on the box, okay? Like I'm going to do it right here. Now, what are all of the other forces? It says, put all the forces. Well, really the only other force that you have is kind of force of friction, okay? And that's going to be opposing the box. So if the box is sliding downwards, okay, so this is motion. Again, you can designate that in the free body diagram. So that means that this is going to be the force of friction that you have, and it's going to be opposing your actual motion. Now, they didn't say neglect air resistance. I mean, there's not going to be much air resistance in here, but there's going to be a little bit. So you can certainly draw, okay, that air resistance there. Well, it's not letting me. There it is. Okay, so this is going to be the force, and this is still friction, okay, but it's going to be the air resistance, okay, that you have. And that's, again, it's going to be opposing it. I mean, technically, if you would draw it, the air is actually going to be hitting right here, right? So, you can certainly put a force which is going to be in the opposite direction, but we, typically will stick it up in the back. But whatever you choose is fine. You can certainly draw this kind of in this direction, that it's just showing that it's the air resistance that you have. And that's pretty much it. Okay, so I don't think that there's going to be any other forces that your teachers are going to look at. And even this one, you probably could have neglected, but since they said all forces, so I'll leave it in there. So that's your free body diagram. Okay, so that's question number 1. Here is question number 2. So consider the following free body diagram. So now they actually give us a body diagram. And it's not a pretty one, because you can see that the forces on the object are at certain angles. And now we want to be able to use graphing and scaling to find the net force. So notice you have 300 newtons, 500 newtons, 600 newtons at certain angles. Okay, so finding this will be kind of difficult because of the fact that they're at angles. So this is a mean question, and it really just tests your understanding, okay, with regards to trying to graph and scale, and then you want to find your net force, which is basically your total force, so the resultant force that you would have. So let's try this out. Now, you're going to have to take out a ruler, you're going to have to take out a protractor if you're going to be actually graphing these. You're not going to be calculating through the components of x and y. So let's, do that directly. So I have a ruler right here that I'm going to do, and I'm going to have to pick a scale. Okay, so let me bring out a ruler, and I'm going to just, actually, I'm going to try to measure one of these. This is 3. So it looks like it's about 3 centimeters there that I have, and it's giving me, an angle. So notice this is 25. This is actually pretty good. So yeah, it's about 25 indeed. Okay, so what I have, let me bring this down. So I'm going to have a scale. So that means 1 centimeter, okay, is going to be scaling to 100 newtons. So that means 3 centimeter, just what I measured right now, was 300 newtons. Okay, so that's what I would have had. Now let me draw these out. All right, so I'm going to try to draw this. This is going to be the first one that I draw. Okay, so maybe let me label this. This is going to be my force F1. And, okay, so this is at 25 degrees, and it's about 3. I'm going to skip the arrow for the moment. But that's going to be my vector, all right? So it's kind of going downwards in that direction. Okay, so I'll put a little line here. Okay, so that's my line right there. Now I'm going to move over to the second one. Now which one you choose as second doesn't matter. This is going to be my force F2, so I'll label this one. Now we have to measure it. Okay, so again, so take out your ruler here. It's about there. Looks like it's about 6. All right. 6 right there. There we go. Okay, so that's fine. So now I'm going to have to start from the other. That's going to be right there. Okay, let me attach it. Okay, that's at, so notice the angle there, it says 135 on the protractor. Okay, so that's what you're, seeing. Okay, right here. Okay, so, sorry, that's what you're seeing right there. Okay, so that's the protractor that I have. It's not letting me because of the ruler. There you go. So that's at 135, which basically means that it's 45 degrees, right? Because that's 180, 180, okay, and then 135. So if you subtract, you're going to get your 45-degree angle. So this is going to be 6. So I'm going to just draw this out best I can here. All right, so there's my 6. Okay, oops. All right. And now I need my last one. Okay, so that's going to be this one. And it's 500, so it's probably going to be 5. I hope so. Everything is... Yep, there it is. It's 5. So that's pretty good. Okay. So that's 5, and then it's at 45 degrees. So we're going to attach it. 45, and we're going to draw 5 right there. Okay. So now that we're done, so what we have is, okay, so this is my, first vector, my second vector, and this is my third vector, okay, right there. So that's what I had. And my resultant vector, so that means, you're going to be starting from here, and you're going to be going all the way over here. So that's going to be the resultant vector, and I'm going to just shift it out so you can see it. And I want to be able to measure it. And what's nice about this is it's going to give me the actual angle as well, so I can measure this with the angle. I love this tool. Okay, so it's about, hold on a second. Yeah, okay, 159. So this looks like it is, so it's going to be 1, 2, 3, 4, 5. It's about 5, it's a little bit less. Oh, okay, well, okay, I couldn't, if I zoom in then it won't work, but this was around, well, it's around 5.4 something, I don't know, I'll put 2 newtons. And I'm guessing here, right? Sorry, newtons, this is centimeters. Okay, so this is centimeters. So that means if I scale it, and that's going to be about 542 newtons. Now, technically, notice that all of these had, so this one, and this one, they all have only one significant figure. So really, if I rounded this, it's going to be 500 newtons, right? But I'm actually not going to round it. I'll try to keep this, okay, at 542. If you wanted to round to only 1, then this is what it would have been, okay, and now recall, it was at 159 degrees. You can go back to the video if you wanted to, okay, see it, okay, or rewind, which means, so that's going to be what, 21 degrees, right? So starting from east going south. So that's going to be the direction, and here it is, okay? So that would have been your answer, and if you want it a lot closer, so it's going to be 542 newtons, and that's your vector. So here's your vector, right? That's the resultant vector that you have right there. So this is your F net, and that's what it would be pointing. So that's question number 2. So this is actually a really nice question. It forces you to work with these with a ruler and a protractor. All right, so let's continue on. Number 3, confirm your answer of the previous question by breaking down each vector into its x and y components. Okay, great. So that means we got to redo the question, but now find the F net well, that's going to test our ability, how well I was actually graphing these and scaling. Okay, so let's recall this. So this is just for reference. It was 542 newtons, and the direction was starting from east, 21 degrees south. All right, so that's what we got by graphing and scaling. Now we're going to break it down into components. So we're going to have, so my first one, which was 300 newtons, and that 300 newtons was 25 degrees. So that was starting from west, 25 degrees. Now I'm saying west. You know, there's really no directions there, but I'm just creating those directions for myself so that, you know, you can say that it's, you know, that 25 degrees, you know, you can add it to 180 plus 25, whichever way you want to do it is fine. This is just for reference for me. So that's the first one. So it's going to have an X component and a Y component. Okay, so, you know, so it's basically something like this. And that means it's going to have, so here is your X and your Y. So that's your X component and your Y component. This is 25 degrees. So you're going to have to do your sines and cosines to be able to find this. All right, so this is going to be 300. Now X is going to be negative. Notice because it's to the left. So that's negative 300 times, and it's going to be cos, okay, of 25 degrees. Your Y component is down, so that's also negative, except this is going to be sine of 25 degrees. Okay, so that's your first one. Your second one that you have, so F2, so let's take a look here. So I think I made this one 600. Right, and this one was starting east, 45 degrees south. Yep, okay, so that's this one. That's what I'm doing there. So now its X component. So this is going to be, sorry, it's like this. So again, well, X is going to be, so that's your X, that's your Y, right? This is 600. We have the angle here, 45. So that's going to be, so X is positive because it's to the right. It's going to be cos 45 degrees. And then your Y component is going to be 600. Now this one is down. Notice it's down, so it's going to be minus. It's going to be sine of 45 degrees. So that's the, and then your last one, which is going to be F3. Now, of course, you can compute these out. I'm not computing it because I'll just do that computation in one step to get my X component of the net value, right, of the F net, my Y component of the F net value, and then I'll have both of them, and then I can create the actual F net to compare to the last one. This one is 500 newtons. Sorry, and this one was from east, 45 degrees north. Okay, again, I'm just making up just so that I know which way I'm going. Okay, so X, so in this case, your X component, so that's going to be 500 cos of 45 degrees. It is to the right. And your Y component is also 500. Now it's going to be sine of 45, although cos 45 and sine 45 are equal to each other, and that's also going to be positive. All right, so now we have all our X and all our Y. So what I'm going to do is I'm just going to add these up. All right, so I'm going to take this, take this one, and take this one. So that's going to be my X. And I'm going to take this one, and this one. That's going to be my Y. So let's see what we will get. And I'm going to do that in fast forward fashion. You can take out your calculator and you can follow along. Okay. Okay, so there you have it. Let me just get rid of this. Okay, so those are that's your X component of Fnet, and that's your Y component. So now, okay, so we can bring these together so we can find out what the magnitude is, okay, between here. So in order to find the magnitude, so the total magnitude of F net would have been, and this is by Pythagorean theorem, right? So you basically take the square root, okay, of F net of the X component, square that, plus F net of the Y component, and you square that. Okay, so we're going to be squaring these. Okay, so let me do that. And again, now in fast forward fashion, let's see what we get. All right, so that's actually pretty good. So 543 newtons. Notice that we got 542 newtons by graphing. So this is pretty phenomenal that we were that close. So that's that. And again, if we would have rounded this to one significant figure, then of course it would have been just 500 newtons. That's the magnitude. Now, if you want the angle, so, finding the angle itself, well, you have, so here is your, your X component. Here's going to be your Y component, right? So this is going to be 505 approximately, 0.9, etc. Okay, this one is down, so it's 197 point, etc. And now you want to be able to find what this angle is. So this one, so that's going to be opposite over adjacent. So you have to take 10, okay, the inverse. So it's going to be 197 point all over 505 point, etc. Okay, so what will this give us? So again, let me just do this in fast forward fashion. All right, so there it is. Actually, that's amazing because it's 21 degrees and this is exactly what we got, right? So starting, now I'm saying from the east side, so it's 21 degrees down. So this is really good. So basically this one is just by using just regular calculations, okay, in trigonometry, and the other one was using your graphing, and they're pretty damn close, which is pretty good. Okay, let's move on. Next question. Here's question number 4. So this is a pretty neat one. This one shouldn't take us too long. So we have a figure. We want to obtain what the tension, okay, is in the rope. Okay, so in rope A, in rope B, and in rope C. So, how do you tackle these ones? Okay, so let's start it off. Maybe what I'll do is this. Okay, so for the tension in rope A, so, this is going to be the force of tension in A. So that particular force, so what you would have, you're going to be grouping these 3 together because so this rope right there has to withstand the mass of all of the actual other ropes, or in that case, their weight. So you're going to have to combine them. So this is, if you were drawing a free body diagram, you would have to say, 1.7 plus 2.4 plus 3.8. Okay, so that's what this would be, and that means your force of gravity, okay, so overall is going to be all your masses, so 1.7 plus 2.4 plus 3.8, right? So this is your mass. Now this is your mass total, okay, mass multiplied by gravity, right, or the acceleration due to gravity, so that's going to be 9.8. So that's going to be that. And now your tension, so in that rope, so basically it has to oppose it and it has to withhold. So it's going to be equal to the force of gravity. So that's what you will have in there. So this tension, okay, is going to be in this direction, right? So it's kind of pulling it up and withholding it. So if you were to take out your calculator, so let's see, so 1.7 plus 2.4 plus 3.8, and then multiplied by 9.8. So that's going to be 77, and I'll just round this, so 2 significant figures. That's what we have in all of them. So that's the actual force. So that means this is your tension force. Okay, so approximately that much. So that's how much it would have to withstand. Now, for B, well, I think you kind of get the idea. So for B, so if I copy this, I'm going to duplicate and do B on the other side. Well, for B, so this particular, so this one, So the tension has to withhold these two. It doesn't have to do anything with that, right? So it has to just withhold these ones. So that means I can erase this. Okay, so it's only going to have those. And so therefore your force of gravity is going to be different now. So this one, okay, so this is going to be the force of tension for B. And that is going to be, okay, counteracting the force of gravity here. Okay, and I'm going to put B here, and I'll put A over here. And so this is going to be just two of them. So let me just shift this out ever so slightly. Put that. And so this is now 2.4 plus 3.8 times 9.8. All right, so what would that be? So 2.4 plus 3.8 times 9.8. So that's approximately 61 newtons. And that's going to be your force of tension here. So there you have it. So that's B. And then for C, well, that for C, it's going to be even easier. So this is going to be the force of tension for C, right? So here, if you were doing that, well, in this case, I'm going to just draw it as it is. So this is 3.8 kilograms. So you're going to have a force of gravity right here, which is just going to be pulling it down, and your force of tension is going to be holding it up. Of course, these should be perpendicular here, or opposing each other. So that means this force of gravity is going to be on C, is going to be nothing else but just 3.8 times 9.8. So 3.8 times 9.8, so that's about 37 newtons. Okay, so that's this one. And there you have it. Okay, so that would have been all the actual tensions, okay, that you would have in your rope. So this is a pretty neat one and forces you back to understand tension. So here's question number 5. It says, in the previous example, if rope B snapped. Okay, well, really, actually I won't even need the mass. Neglecting air resistance, so everything, we don't really even need the mass in here. Then what would be the speed? Okay, so it's just asking us for speed, okay, of the two masses that broke off. So this is going to be falling down, right? That's going to be falling down. So gravity, so 9.8 meters per second squared. We know that this is down. So what would be the actual speed in here? Well, the initial speed, so we're going to be assuming that the initial speed was just 0 because of the fact that I guess the rope was holding it down and then it just snapped, right? So it went from nothing and then it started going. Now they're telling us this is after 2.5 seconds. So after t is 2.5. So now you have to go back to your kinematics equation. So this is going to be your V final is equal to your V initial plus your acceleration times delta t. So you can go back to those equations if you don't remember or recall. So this is what we would have. And now if you're substituting all of this in, well, this is just 0. Now notice, if we assume down, okay, is negative, so, you know, I can assume that, I guess. So it's going to be plus negative 9.8. And this is going to be 2.5. This just really will tell us that, you know, the speed, it's not really negative. It just means that it's going down because I chose up to be positive. So that means 9.8 times 2.5, and that's 24.5 meters per second. This just means that it's down. So whatever convention that you choose, all right? So you can do that. And this would have been with respect to up being positive. And if you wanted to make it, you know, so V final, you can also say that it's 24.5, you know, meters per second, and you can put it down, and that's the same thing. Well, I guess rounding it, so it should have been 25 to two significant figures. So that's it, actually. So there's nothing really else for this one. So this one was really simple. At least I hope, and it gives you some idea on how to approach this one. Okay, let's keep going. Here's question number 6. Okay, so this one is neat. Let me switch colors. Okay, so a patient on a bed has been accidentally let go by a patient porter. Okay, so let go. Well, I'm assuming. Okay, so this should be maybe a little bit clearer, but I guess it's clear enough. Okay, so here's a patient. So here's we have a patient lying down. They're on a bed. Let's say this is moving in this direction. Motion. Okay, so they have been let go. Okay, so maybe something happened. Maybe it slipped. Okay, and obviously if you're moving, then it's going to still continue to move, right? Unless there's just an enormous amount of friction, that this thing will just stop. But here it says originally the bed was moving. So notice that initial velocity was 1.15 meters per second. The bed with the patient on it has a mass. All right, so this thing, so I'm going to just draw this down. So force of gravity. Okay, so this is going to be 280 kilograms times 9.8. Not that we need it, or we may need it, I'm not sure, but okay, so that's my mass. Okay, so that's mass right there. The force of friction, okay, so there is a force of friction, so that's going to be in this direction. So force of friction is 240 newtons. How far would the bed and the patient move before stopping? Okay, so this is going to take us a little bit of time. So what they're asking us is for this bed, okay, sure there is friction, but they're moving. So that means it's going to move a certain distance. And we want to find out what that distance is, really. So that's what we're after. That's ultimately what we want. So this is going to be what we want. Okay, so we want this. Now, because there's force of friction, so that means the bed is eventually going to stop. So now you can start thinking about, okay, well, that displacement or the distance covered, you're going to have to go back to kinematics. There's going to be an acceleration. In fact, it's a deceleration. Okay, so it's a deceleration because it goes from 1.15 meters per second to 0. Right, so it starts to decelerate. So we need that acceleration in some way, because in order to find this, okay, so you kind of have to go back to this equation. So VI times delta t plus 1/2 acceleration delta t squared, right? So now if you put all of these, although we don't really need vectors, we kind of know it's I'm assuming that it's moving to the right, but whichever way you assume is fine. So you can drop the vectors in there. Okay, so now, okay, if you're taking this on, so I have this, I don't have this, right? I don't know how long it took to stop. I actually don't know acceleration either, right? So I am missing 2 pieces. I have to find those pieces somehow. Well, the acceleration, so that is from Newton's second law. So, maybe number 1, let's find the acceleration. Okay, so let's do that. Now, how will I find that? Well, F net equals to mass times the acceleration, right? So that's what I know. Now, I know the mass is 280. The acceleration is what I want. Do I know F net? Well, what is F net? Well, the only force present, notice, in here is the force of friction, right? So the force of friction is in the opposite direction. So F net really is just negative 240 newtons. That's what that is equal to in the opposite direction. Your mass is 280 kilograms. That's all together. And that is multiplying the acceleration. So at least, so the magnitude we will know. The direction we'll know as well. It's decelerating, right? So acceleration Okay, if you're moving in this direction, it's actually, you know, negative means it's that way. It's decelerating. So the acceleration here is going to be negative 240 all over 280 meters per second squared. Now you can, I'm going to get rid of this, right? Actually, I can simplify this even further. So that's going to be what, 12, 14. So what's that? 6 over 7. Okay, so that's negative. You can find out what that is, okay, if you wanted to. So you can certainly do that. You know, 240 divided by 280. I just don't want to work with that. So 6 over 7, yes, all right. Let me just keep it in fraction form because I don't want to keep those decimals. So that's my acceleration. So that's check, okay, great. So now I have, so let me just show you. I have this, I have now this, so the only piece I'm missing is this, delta t. So that would have been my second item, so number 2. So how do I find that? So I want to find the amount of time it took. Now, that I can find from the fact that acceleration is the change in velocity over the change in time. Now, why do I want to use this? Because acceleration I know, so that's negative 6 over 7 meters per second squared. Delta V, so please recall, this is V final minus V initial, but V final is 0, right? Because it's going to stop. So this is going to be 0 minus, okay, and this was 1.15. And voila. So now we're only missing delta t. So I can solve for this delta t. So delta t will be equal to, so you can bring this over, right? So you can multiply both sides. Okay, you're going to have this divided by this. And that's going to be your, so negative 1.15 all over, it's going to be 6 over 7, negative. So the two negatives cancel. And here, unfortunately, I'm going to be stuck. So let's see. This is 1.15 divided by, 6 over 7. So there we have it. Well, I'll just keep it as a, this is what I mean by being stuck. I kind of have to keep these in here. Okay, I'll round this. So 1.342, okay, approximately. You can keep more decimals if you like. So that's going to be how long it took for that bed to stop. All right, so now I have everything. So if I go back in here, okay, I'm going to put in an extra page. So if I go back in and I now take this, okay, this is what I wanted. So copy it, bring it down. This is my final step. So now I can substitute everything in. Just can't forget this is squared. So let's put it in. So this is 1.15. The time is 1.342 plus 1/2. The acceleration is negative 6.6 over 7. And then, so again, 1.342 squared. All right, and now you can compute it. Okay, so I'm going to just plug it all in and let's get our answer. All right, so it's about 0.77 meters. So it doesn't go too far, right? So it's a pretty heavy bed, okay, and the friction that it had, okay, was sufficient enough that it just kind of let it slide. Now, hopefully it's, 0.77 is very close to a meter. It's about 3/4 way to a meter, so hopefully it didn't hit anything or anybody as it was rolling along. So that's a very nice question. This really will test your understanding of forces, okay, and kinematics together. Okay, so this is a fantastic question, and I'm not sure how many students would have got this in an introductory grade 11 physics class, but if you did, huge thumbs up to you. Here's the last question. Okay, so let's take a look at this one and see what this is all about. So Jason, they give us a weight, which is 175, well, right away. Okay, so please don't forget that you have actually, 1 Newton. So 0.2248 pounds. All right, so we have that in between them. Okay, so that's the weight, Jason's weight. So lives on the 30th floor of a condominium. Okay, so he walks into an elevator which begins to move down. Okay, so this is going to be an elevator problem. So notice A, B. All right, well, let's draw this in. Okay, so that's my elevator. So let's do a free body diagram here. Okay, so this is going to be down. So that's Jason. So this is the force of gravity or the weight, whatever you want to label it as. Okay, so that's 175 pounds. Now, we don't really want it in pounds if we want SI units, but I'll leave it at that for the moment. All right. And now, okay, so this is, okay, so free body diagram again. So this is going to be, now technically, you know what, I mean, this is what's happening. So if Jason is here, right, so this force right here, maybe I'll put it where it should more or less be. It basically, so at the feet there, okay, that you have, this is what Jason is going to be feeling, right? It's going to have some kind of a force here. Now, the question is, it's going to be smaller or bigger than his actual weight. Now, you're moving down, and you can probably sense, right? So if you walk into an elevator and you're going to start to move down, you do actually feel a sense of being a little bit lighter, right? Because you're going kind of down with gravity as you're moving downwards. But let's check this out and let's see what happens. Now, the acceleration of the elevator is 2.8 meters per second squared down. All right, so we have an acceleration in here. So this is 2.8 meters per second squared. So this is down. And now what are they asking me? What is the apparent weight that Jason feels during the acceleration? Okay, so that's basically this. This is what they're trying to find out. So that's your force of normal. That you have. Remember, force of normal is at the contact point and always perpendicular to the contact point, so it's up. And those really are the only two forces. There's no other forces that we know of. You know, there is friction and stuff, but I guess we're neglected because they don't mention anything else. Okay, so let's take a look and see. So how would we handle this question? Okay, so this would mean the following. So F net is going to be equal to mass times acceleration, right? So that's what we have. Now, I guess we do have to know the mass. Okay, so this will come out from here. So this is the weight. Okay, so within there. So you may or may not. So 1 kilogram is approximately 2.2 pounds. And you can get that from the equation. You know, you can manipulate this if you wanted to. Okay, so this is a conversion ratio. You can assume that this is, you know, kind of given, okay, within here. If not, you can find it. So what does that mean? So 175, if you want it in, so you have to divide this by 2.2 and you're going to get, so this is approximately, so it looks like Jason's about 80 kilograms. So 79.545, etc. Okay, so 5454. So this is that. All right, so that's kilograms. Now, we know the acceleration. So we know this. We know the mass. So we know F net. Okay, so this is known. So I can certainly compute this out. So this is going to be answer multiplied by 2.8. All right, so we have about 222.72 newtons. I'm going to leave it. I won't round it yet. So that's my F net. Now, F net, of course, is the summation of all the forces, right, that you have. Now, the way that I've done it, because notice that it's down, so this F net is down. So I'm going to assume, because we're moving down, that down is positive, right? So if you assume that down is negative, okay, and up is positive, then the 2.8 meters per second squared would have been actually negative, right? If you did that as a convention. I'm going to just assume that down is positive. So if down is positive, then this is going to be equal to the weight, and then minus the apparent weight, right? We're after this. This is what we really want. We already know what this is. Now, we already know what this is as well. We know the weight, okay, right there. It's 175 pounds. Now, in newtons, we can certainly do that. Well, since I've already computed, okay, so this is going to be, in terms of newtons, to 79.545454, etc. So times 9.8. So it's about 780, it looks like. So that's right there. So we know this is going to be 222.72 equals to my weight, which is 779. I mean, you don't have to be this accurate in here. Hopefully your teacher won't be that mean, but it did say don't round in intermediate steps, okay, at the top, so I'll just leave it. So now solving this, so that means Fn is equal to 779.54 minus 222.72. And then you'll get your answer. So you're going to get your answer minus 222.727272, etc. So now I can round. So let me round it. So 500, approximately 60 newtons. That is the apparent weight. This is what he feels. Notice that it's less than his actual weight. And again, that should make sense to you, because when you're walking into the elevator and it takes off downwards and starts to accelerate, it's almost like you feel a sense of a lift. You feel a little bit lighter. All right, so this is what the apparent weight would be, 560 newtons, right? And this is up, of course. Okay, so this is what it would have been. All right, so now for part B, what would be the apparent weight once the elevator continues downward at a constant speed? For this, you don't need any actual computation. Constant speed means you're under Newton's first law. So under Newton's first law, F net is equal to 0, which means that your net forces cancel each other off. So that would mean that your weight, and your normal force, because they're in opposite directions, must cancel each other off, so they're equal to each other. And that is true, right? When you're walking around, if you're just standing in an elevator, if it's moving at a constant speed by Newton's first law, your apparent weight, so your normal force, is going to be equivalent to your weight itself, okay? So that would have been part B. So basically, the normal force or apparent force is equal to your weight, okay? Your regular weight. So 175 pounds. All right, so that would be it. All right, so that's a pretty awesome test in here. Okay, pretty lengthy, really good questions, and hopefully that got you started. Okay, so if you were studying, you now had a good test for yourself on these topics. Okay, thanks for watching. See you in a future video. Bye, everybody.